Welcome AP Statistics students to another fun and exciting day of virtual learning. Does life get any better than this? So today's topic is correlation. Now you should have seen this in Math 1. It's part of the state framework for Math 1 curriculum, but who knows if you took Math 1 in middle school, if your middle school teacher covered this or not. But luckily, I am here to help you out. So today I'm going to go over correlation. We abbreviate correlation with the letter R, lowercase r, if it comes from sample data. If it's an that makes it a statistic. If it's a parameter, meaning it comes from the entire population, if it's the theoretically, perfectly accurate correlation, we use the letter rho, Greek letter rho, but we're not going to get into that today. So today it's just going to be R. Okay. Here's the formula to calculate correlation. Okay, in our previous lesson, you would make a scatter plot and you would just kind of eyeball, hey, it looks like a line or doesn't look like a line, or it's kind of a line, right? We didn't really have a formal way of judging how close the data fit a line. This is a formal, objective measure of how close the data fits a line. And that's very important because our eyes are a little bit subjective. Obviously, the viewing window that you use to look at your graph, right? If you zoom in, the points look further apart. If you zoom out, the points look a little closer together. So our eyes can be fooled. Very subjective to just look with our eye. We should start there, but to get an objective measure, here is a calculation for that. This formula is also available on your formula sheet right here. So as always, you don't have to memorize this formula. It's given to you on the AP exam, right? Because this is the sheet they give you when you take the AP exam. Just walking through the formula, make sure you know all the parts. Remember lowercase n, that's how many, in this case, ordered pairs you have, right? It's the sample size of your data set, and this is XY ordered paired data. Remember this sigma, that means I'm going to add up, right? It's the summation. And what I'm going to do is I'm going to take each x coordinate minus the mean of all the x coordinates, going to divide that by the sample standard deviation of the x coordinates. Okay, and then I'm going to multiply it with the corresponding y coordinate. And again, same thing. The first y coordinate minus the mean of the y's divided by the standard deviation, sample standard deviation of the y's, and then do it for the second, and so on and so forth. So each xy gets multiplied together, and then we're going to sum up all of those products. Then we divide it by n minus 1, and that will be our correlation. Okay, some facts about correlation. In other words, how do I interpret this R value, this calculation that I just did? The sign of R is very important. It tells us the direction of the association. So if I see points going in a positive, right, with a positive slope or a positive association, then I will get a positive R when I calculate my correlation. Okay, if my trend is negative, right, negative slope or negative association, then when I calculate R, I will get a negative value for R. So the sign on R tells you the direction of the association, which is awfully handy. Okay, now R, we just mentioned it could be positive or negative, but it always lies between -1 and +1 inclusive. So if I have a perfect set of collinear points, let's say those are 3 collinear points, that would be a perfect positive correlation. I would get 1, right? Same thing for 3 collinear points with a negative slope. I could get a correlation of exactly -1 only if they're collinear. As soon as I have any variation, right, I have some point that's a little bit off, now my correlation's no longer going to be exactly 1 or exactly -1 if it has a negative slope. Okay, So the closer your correlation is to 1 or -1, the stronger your data fits a straight line. Now, the further you are from -1 or +1, or in other words, the closer you are to 0, the weaker your relationship, the weaker your correlation or strength. Now, don't expect to see 0. To get 0 is very difficult. You almost have to kind of set it up yourself and create like some type of like square or something. As soon as you have a little bit of something happening, you won't get 0 anymore. So don't expect to see 0 pop up unless you almost purposefully place points yourself to create a correlation of 0. So really what we do, anything at all close to 0, we say there's nothing there. There's no relationship. Okay, now, this is really important. When I change units, right, let's say I change from inches to centimeters, feet to miles, Celsius to Fahrenheit, meters to whatever, it's not going to change my correlation because my correlation is using standardized observations. So go back, right? I'm dividing the x's by the standard deviation of x. I'm dividing the y's by the standard deviation of y's. So these are standardized, number of standard deviations. So if the numerator was inches, the denominator was inches. Inches over inches cancel, and this is a number of standard deviations. If I change to centimeters, it'd be centimeters over centimeters. It would still cancel. So it's still just number of standard deviations, or in other words, standardized value. So it doesn't matter if I convert my data from one unit to another, I'll still, in the end, get the same correlation because the units will always cancel in this calculation, which is really cool. Okay, next. The correlation, this calculation, measures the strength of a linear relationship. Okay, so if you have a curved relationship, which we will get to in chapter 4, this calculation will be fooled, right? Because this calculation is looking, is it a linear relationship? Now, when we get to chapter 4, we'll see how to take a curved relationship and transform it to a linear relationship, right? So if we can figure out the curve, if it's exponential, right, we can use logs because logs are the inverses, and then that'll linearize it. If it's quadratic, we could take square roots, right? That'll linearize it, so on and so forth. So when we get to chapter 4, we'll learn how to take a curve and make it linear or approximately linear, and then calculate the correlation. Okay, so just remember, we use this for linear relationships only. And lastly, correlation is not robust. Remember that vocabulary term? Right? It is not robust. So in other words, extreme observations will affect the correlation. And there's two types of things that can happen. We can get an outlier, which will weaken my correlation, or we can get what we call an influential point, which will strengthen my correlation. Let's talk about that briefly right now. So let's say I have a data set that looks like this. Right now, it's pretty darn linear. I'd have a pretty strong correlation. It'd be pretty close to 1, okay? But if I add a point like this right here, I've now weakened that relationship, right? Because that point doesn't follow the overall pattern of the other data. So this is called an outlier in bivariant data, bivariant, two variable x, y. So that would be an outlier for bivariant data. Okay, and the way you tell that it's an outlier is because it has a large vertical distance from the other points in its neighborhood, right? In its x neighborhood. In other words, here's a word we're going to talk about more later, but it has a large residual. The magnitude of the residual, not direction, magnitude. So large residual means outlier for bivariant data, and outliers will weaken the correlation. Now, let's look at another data set. let's say I have kind of just a blob of data, lots of points together. Okay. Right now, there's not really a whole lot of correlation. It's just a blob. But if I add 1 point, say over here, my correlation goes much stronger. So from like this, right, it's a blob. The correlation is, approximately 0. It won't be exactly 0, but it's low, it's weak. I throw this 1 point in, and now all of a sudden, I could fit a line here, and it fits the data pretty close. And my correlation's relatively strong, all because of that 1 point. So that 1 point is called an influential point. Okay. Notice the influential point, when you draw your best fit line, will actually end up being very close to the line. Without the influential point, who knows where my line would go, right? But with the influential point, it pulls the line right to itself, and that will thereby strengthen my correlation. The outlier, on the other hand, without the outlier, I have this line. With the outlier, I still have a fairly similar line, but now I have 1 point that's a long way away from the line. So the outlier doesn't pull the line to itself that much. It changes the line a little, but not a ton. However, it's a long way from the line vertically. Right? The influential point, it's a long way from the other data horizontally. That's what allows it to influence the line so much. Right? If I threw a point real close, now it doesn't influence the line as much. Right? It has to be horizontally a great distance from the other points. Okay, so those are the two types of extreme observation that we have. But they both obviously have a large impact on the correlation calculation. One weakens, one strengthens. Okay. Let's try an example. Okay. So here's a very simple data set, 3 points. Notice you have to have at least 3 points, or if you have 2 points, a line will go through 2 points always collinearly. So with only 2 points, you'll always get a correlation of either 1 or -1. Okay, so here's 3 points. Let's calculate their correlation by hand. Just looking at the points, 2, 4, 6, 7, 8, 9, you can already see they're all 3 collinear, so and a positive slope. So I already know the answer to this is going to be R equals 1, correlation of 1. But let's calculate it by hand. And if we don't get 1, we'll know we made a mistake. If we do get 1, we'll know we did it correctly. Okay, so first, get your summary statistics, right? What's the mean of the x's? What's the mean of the y's? How many points do I have? Or in other words, sample size. Okay, now I can plug my information into the formula, right? So n is 3. And then up here, I'm going to go through each point one at a time, right? So my first point, the x-coordinate is 2 minus the mean of x divided by the sample standard deviation of x. I didn't write that down, but you can calculate it. It's 2. Here's the fast way to do it. Okay, so enter the data, right? Here's the, whoop, that's not the data. Shoot, I don't have the data entered. So we'll just calculate it by hand real quick. Okay, so sample standard deviation. Remember, we're going to take each point minus the mean squared. We're going to divide by n minus 1, and we're going to square root. Okay, so that's how we got. The sample standard deviation is 2 for x. Okay, you can go ahead and repeat that same thing for y, and you'll get the sample standard deviation for y is 1. Okay, so that's just a quick review from chapter 1. All right. So what I do, I take the first x minus the mean of x divided by the sample standard deviation of x. And that gets multiplied with the first y coordinate minus the mean of y divided by the sample standard deviation of y. Okay, that's for the first ordered pair. Then I do the second ordered pair, and I'm going to add these together. I'm finding the summation of all of them. Okay, so for my second ordered pair, second x minus mean of x over standard deviation of x, second y coordinate minus the mean of y over the sample standard deviation of y, right? And then plus, repeat for the third coordinate, plus the fourth, fifth, sixth if they have more coordinates. And you just continue to do that. So that's the summation part. Work it out. And in this case, sure enough, we get 1, as we should get 1. So we did it correctly. And that's how we do correlation by hand. You're not going to do it by hand very often, though, because it is kind of tedious. Okay. Now, if you do want to do it by hand, I would suggest using this formula. I did take this class in college, and my professor said no calculator, so we had to do it all by hand. And this formula that's given, it's not very nice to do it by hand. On my example, it worked nicely because I purposefully picked 3 nice, clean points that ended up with means that were whole numbers and standard deviations that were whole numbers. But normally, it's very common for your mean to be a fraction, right? And it's extremely common for your standard deviations to be irrational. So you're ending up with a fraction divided by an irrational number times another fraction divided by another irrational number, and you're going to add all those up. So doing this by hand for most data sets is really not nice. It's very tedious. This method is much easier if you want to do things by hand. Bad news is this is not on your formula sheet, because the formula sheet is assuming you have a calculator at your disposal. But if you don't want to use a calculator, I would suggest memorizing this formula. On the surface, it kind of looks not as nice as the first formula, right? It has more components, but I'll show you why it's nicer. And by the way, we call this formula the Pearson product moment correlation coefficient, in honor of Carl Pearson, who developed correlation. So the way it works is you take the sample size, you multiply it by the summation of the x times y minus the summation of the x coordinates times the summation of the y coordinates. There's your numerator. Denominator is the square root, sample size multiplied by the summation of the x squared coordinates minus the summation of the x's squared. And then that same thing for the y's. So the square root of the sample size times the summation of the y squareds minus the summation of the y's squared. So I'm going to do this for those of you that are interested in taking the class without a calculator. So again, I would make a table if I did this by hand. List out my ordered pairs and then add a column, x times y. 2 times 7, 4 times 8, 6 times 9, so on. Add a column for the x squareds, 2 squared, 4 squared, 6 squared. Add a column for the y squareds, 7 squared, 8 squared, 9 squared, right? So you can see, very easy to do that without a calculator. Because typically your x and y values are going to be, they're not always whole numbers, but they're normally fairly nice numbers to work with, so this works out pretty nicely. Okay, then add a row to find the sum of each of those. So sum of the x's, sum of the y's, sum of the x times y, sum of the x squared, sum of the y squareds. And then plug into that Pearson product moment formula. And you can see it comes out pretty nice without a calculator. Okay. And again, you get the same value. So those of you that are math nerds, maybe you've had your calculus already, right? And you're just taking this because it's the only class left in high school. How about take that formula and prove that they're equivalent? Hey, that's something fun you could do. That's not part of the scope of this course, but that's the kind of thing you could do just for fun. All right, so you now have 2 ways to find the correlation. Let's practice. Our class being an introductory class, we're not doing a lot of proofs, if any. and we're just, we're just accepting these formulas, and we're using them, we're applying them to problems, and then we're interpreting the problem. That's kind of what this class is all about. So here's a problem. Take a look. Let's see if you can see if there's a relationship between age and blood pressure. Okay, so first thing you want to do is enter the data in your calculator, which I've done. Then ask yourself which should be explanatory, age or blood pressure. Okay, does a person's age explain their blood pressure, or does a person's blood pressure explain their age? Okay, so hopefully you conclude age is the explanatory variable. It should be graphed on the x-axis. Blood pressure is the response. It should go on the y-axis. Before you calculate correlation, you should always take a look at the graph. Use your eyeball and make sure it looks fairly linear, because remember, you shouldn't be calculating correlation on a curved relationship without linearizing it first. So the scatter plot's the first graph choice. We said age is the x, blood pressure is the response, and zoom stat. There's our scatter plot. It's a small data set, but there's nothing in here that looks like, hey, it's curved. So it could be linear. Therefore, I will proceed. So at this point, if you want to get your summary statistics quickly to use your formula, right, you can go to Stat, Calculate, and look at your second choice, bivariant or two-variable statistics. Okay, X is in list 1, Y is in list 2. And there we go. We now have our mean of X. Hey, there's the sum of the X if you want to use the Pearson product moment, and the sum of the X squareds. There's your sample standard deviation. Again, it's irrational, like I warned you would happen. Sample size. And then if we scroll down, look, the mean of Y, the summation of the Y, summation of the Y squareds, sample standard deviation for Y, and the sum of the XYs. So it gives you all the information you need to use either of the two formulas. How wonderful. And then it also gives you max and mins. Okay. So that's the quick, easy way to get the information that you can now plug into your formula. But I will show you an even faster way to get R. If you go to Stat, you go to Calculate, you may have noticed we have this linear regression thing here. And just an aside, it appears again on number 8. You'll see the only difference is here A is the slope and B is the y-intercept. Down here, A is the y-intercept and B is the slope. Other than that, it's the same. You could use either one. Just pay attention to which letter you're calling the slope and which letter you're calling the y-intercept. I really have no idea why they're both there. All I can think of is the people making the calculator had an argument. I want B to be slope. No, I want A to be slope. And they fought and fought and fought. So finally somebody said, let's compromise and allow both. That's the only reason I can see why they have both on here. So pick either one. And then you tell your calculator where the X value is, where the Y value is. And I'm going to add one more piece to this because it'll help us on our next lesson. Put one more comma and use this STO, that stands for store. Use that button. Okay. And then I want to store it in my Y equals. So I'm going to store the equation that it spits out right here. So the way to do that is I go to variables, I go to Y variables, I choose function, and I'm going to choose Y sub 1. So now my calculator is going to perform linear regression for me, and it's going to store the result in my menu here, my Y menu. Oops, sorry, didn't need the comma there, just the store button. Maybe not. I don't need the store button, just a comma. There we go. Sorry about that. We'll use the store button later, so I'll show you again. That's the correct entry if you have this calculator. The more advanced calculators will actually have a little thing that says store, and then you put in the y sub 1. But this is the older model, just use a comma. Okay, so I do that, and it does the regression. It gives me the predicted y-intercept, the predicted slope for the line of best fit, tells me r squared, which we'll talk about more next time. And there's r. There's the correlation. Hey, way faster than doing it with the formula. Okay. And sure enough, that matches what I have here. And visually, watch how cool this is. When I hit y equals, it stored the equation in there for me. And now when I graph it, I have my scatter plot, plus I have the best fit line all on one graph. So visually I can see how close the points lie to the line of best fit. They're fairly close, and that's why I have a correlation that's fairly strong, right? Remember, it's not 1 because the points don't all land on that line. They're not all collinear, right? There is some variation from the line, and that's why we're at approximately 0.9, which is fairly strong correlation, positive. Oh, did some of you not get R on your display when you did the linear regression? What a bummer for you guys. Maybe you need to buy a new calculator? Or you could ask the calculator nicely to provide that in its output. Let me show you how to do that. All you have to do so that your calculator will provide you with the correlation when you do a linear regression is turn your diagnostic on. So just go diagnostic on and you'll have it. And yeah, you probably don't know where to find that, right? Neither do I. But before you panic and start Googling it, when I don't know how to find a command in my calculator, I go to the catalog. The catalog lists every single command in an alphabetical order. So I go second, there we go. And here's every command I could put into my calculator, listed alphabetically. And there's a lot. So I'm gonna scroll down. And there it is, diagnostic on. So I'm gonna choose that. Now at this point, my diagnostic still isn't turned on. I have the command, but I haven't told the calculator to execute the command. So I hit enter. Now the command has been executed. Now your diagnostic is turned on. And now if you redo the problem, you will get the correlation. Now, if you ever reset your calculator, the default settings have the diagnostic turned off. So if you buy a new calculator straight out of the package, it will have the diagnostic turned off. So I bet most of you had your diagnostic off when you did this first problem. And that's why we need to turn it on. But in the future, if you lose the correlation because you had to reset your calculator's memory, that's how you get it back. Okay? Pretty cool. All right, let's try another one. This time we have number of absences and a final grade in a class. Again, enter the data in your calculator. Okay. Then ask yourself which variable should be explanatory, which should be response. Does the person's grade explain their number of absences? Does the person's absences explain their grade? Okay, so in most instances, we would say absences should be explanatory. So absences would be my X or independent. Grade would be my Y or dependent or response variable. Okay. I've already entered the data, list 3 and 4. So first step, I'm gonna graph a scatter plot of that data. Again, I choose scatter plot. Absences are the X, grade the y. And zoom 9 for stat. Oh no, that line is still appearing. So go back to y equals, there's the line from the last problem. You have two options. You can turn that off or you can clear it. Let's say you want to keep it for a future calculation. Highlight the equal sign, hit enter. Now the line is turned off. So you can still keep the line for a future calculation. And when I graph, the line's no longer graphed. Okay. Or if you want to clear it, well, then just hit clear. And now it's gone. Okay. So there's my graph. And sure enough, as absences increase, grades decrease. So there's a negative association here. Visually, it appears to be somewhat linear. I don't see anything that tells me it's a curved relationship. So calculating a correlation here seems reasonable. Again, to get your summary statistics, go calculate two variable stats. And here's all that you need to use either formula. Or, of course, the fast thing to do, perform a linear regression. Either one. But now make sure you tell the calculator where the data is. For me, it's in list 3 and list 4. And again, I'm going to store that equation. I could have stored it into the second slot if I wanted to keep that last equation, but I already cleared it. So, and there we go. This time I have a negative correlation, as our eye told us. And it's actually stronger than the last one, right? You can see there's a little less variation around the line, right? In other words, the points are closer vertically to the line than the last graph. And that's why we have a little bit stronger correlation, right? Because the correlation is further from zero. Probably the easiest way to say that. Okay. All right, one more example. This time I collected data on the number of hours per week a person exercises and the amount of milk they drink that week. So we enter that data in our calculator. And now we try to figure out what is the explanatory variable and what variable is the response. This one's not so clear-cut, is it? Does exercising make you thirsty for milk? Does drinking fatty, heavy calorie milk make you need to exercise to work it off? I'm not really sure what the relationship is. And sometimes that happens. You have two variables and there's not really a clear-cut explanatory response relationship. In which case, feel free to try it either way. We'll do that. Let's do it both ways on this example. So we'll start, we'll call exercise explanatory and milk response for starters, okay? Okay, so I've got X is hours of exercise, Y is amount of milk, and there is my graph. Good news, it doesn't really look curved. Bad news, I can't tell if there's a relationship here at all, right? It's just kind of random. So let's perform a regression on this and see, when I have random data, what kind of correlation I would get. And there we go. Our random data gave us a correlation that's basically, we're going to call that 0. Okay? Like I said, anything at all near 0, that means there's no relationship. It's just random points. And it should make sense because these variables really, we couldn't come up with any reason why they should be related. They're not related. So we get just kind of a random scattering of data. And I bet before you did the calculation, you probably thought, maybe a negative, right? Your eyeball probably said maybe a slightly negative best fit line if you were just guessing. That's what my eye told me. But it turns out it's a little bit positive, not a little bit negative. But the point is they're both really basically zero, right? It's basically almost a horizontal line, so no relationship. Okay, so sure enough, we got that right. Now, let's say we switch it around. Maybe it's milk that's explanatory and exercise that's response. So let's try it again. So now I'm going to switch my x and y. Get rid of that equation. And here it is, switching my x and y. It still looks like a bunch of random points. But okay, let's calculate a linear regression. And again, switch your x and y. And hey, look, I get the same correlation. There's the graph. Again, the line's basically horizontal, but it's the same exact correlation. Isn't that weird? Okay, so why did I get the same exact correlation? Is that coincidence? Look at our formula. If I switch x and y, all I'm doing is changing the order of a multiplication. Multiplication is commutative, so it's not coincidence. Switching x and y has no impact on the correlation. You get the same correlation. So if you accidentally mess up explanatory and response on a problem, good news, you're still going to get the correlation correct. Bad news, your equation's going to be incorrect, but your correlation will still be the same. So that's kind of an aside that we like to ask test questions about. Just like unit conversions, what impact does unit conversion have on correlation? None. What impact does switching the response and explanatory have? None. So those are two really nice things about correlation. Okay, hopefully that was a lot of fun. Next time we will move on and look into the idea of residuals. Won't that be fun? Thanks for tuning in and have a good day.